Chapter 15, Part 4 of Volume 2 of Airplane Flying Handbook, FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Dale Latham. Airplane Flying Handbook by the FAA. Pilot sensations in jet flying. There are usually three general sensations that the pilot transitioning into jets will immediately become aware of. These are inertial response differences, increased control sensitivity, and a much increased tempo of flight. The varying of power settings from flight idle to full takeoff power has a much slower effect on the change of airspeed in a jet airplane. This is commonly called lead and lag, and is as much a result of the extremely clean aerodynamic design of the airplane as it is the slower response of the engine. The lack of propeller effect is also responsible for the lower drag increment at the reduced power settings and results in other changes that the pilot will have to become accustomed to. These include the lack of effective slipstream over the lifting surfaces and control surfaces and lack of propeller torque effect. The aft-mounted engines will cause a different reaction to the power application and may result in a slightly nose-down pitching tendency with the application of power. On the other hand, power reduction will not cause the nose of the airplane to drop to the same extent the pilot is used to in a propeller airplane. Although neither of these characteristics are radical enough to cause transitioning pilots much of a problem, they must be compensated for. Power settings required to attain a given performance are almost impossible to memorize in the jets, and the pilot who feels the necessity for having an array of power settings for all occasions will initially feel at a loss. The only way to answer the question of how much power is needed is by saying, whatever is required to get the job done. The primary reason that power settings vary so much is because of the great changes in weight as fuel is consumed during flight. Therefore, the pilot will have to learn to use power as needed to achieve the desired performance. In time, the pilot will find that the only reference to power instruments will be that required to keep from exceeding the limits of maximum power settings or to synchronize RPM. Proper power management is one of the initial problem areas encountered by the pilot transitioning into jet airplanes. Although smooth power applications are still the rule, the pilot will be aware that a greater physical movement of the power levers is required as compared to the throttle movement in the piston engines. The pilot will also have to learn to anticipate and lead the power changes more than in the past and must keep in mind that the last 30% of engine RPM represents the majority of the engine thrust, and below that, the application of power has very little effect. In slowing the airplane, power reduction must be made sooner because there is no longer any propeller drag and the pilot should anticipate the need for drag devices. Control sensitivity will differ between various airplanes, but in all cases, the pilot will find that they are more sensitive to any change in control displacement, particularly pitch control, than are the conventional propeller airplanes. Because of the higher speeds flown, the control surfaces are more effective, and the variation of just a few degrees in pitch attitude in a jet can result in over twice the rate of altitude change that would be experienced in a slower airplane. The sensitive pitch control in jet airplanes is one of the first flight differences that the pilot will notice. Invariably, the pilot will have a tendency to over-control pitch during initial training flights. The importance of accurate and smooth control cannot be overemphasized, however, and it is one of the first techniques the transitioning pilot must master. The pilot of a swept-wing jet airplane will soon become adjusted to the fact that it is necessary and normal to fly at higher angles of attack. It is not unusual to have about 5 degrees of nose-up pitch on an approach to a landing. During an approach to a stall at a constant altitude, the nose-up angle may be as high as 15 degrees to 20 degrees. The higher deck angles, pitch angle relative to the ground, on takeoff, which may be as high as 15 degrees, will also take some getting used to, although this is not the actual angle of attack relative to the airflow over the wing. The greater variation of pitch attitudes flown in a jet airplane are a result of greater thrust available and the flight characteristics of the low aspect ratio and swept wing. Flight at the higher pitch attitudes requires a greater reliance on the flight instruments for airplane control since there is not much in the way of a useful horizon or other outside reference to be seen. Because of the high rates of climb and descent, high airspeeds, high altitudes, and a variety of attitudes flown, the jet airplane can only be precisely flown by applying proficient instrument flight techniques. Proficiency in attitude instrument flying, therefore, is essential to successful transition to jet airplane flying. Most jet airplanes are equipped with a thumb-operated pitch trim button on the control wheel, which the pilot must become familiar with as soon as possible. The jet airplane will differ regarding pitch tendencies with the lowering of flaps, landing gear, and drag devices. With experience, the jet airplane pilot will learn to anticipate the amount of pitch change required for a particular operation. The usual method of operating the trim button is to apply several small, intermittent applications of trim in the direction desired rather than holding the trim button for longer periods of time, which can lead to over-controlling. Jet airplane takeoff and climb. All FAA-certificated jet airplanes are certificated under Title 14 of the Code of Federal Regulations, 14 CFR, Part 25, which contains the airworthiness standards for transport category airplanes. The FAA-certificated jet airplane is a highly sophisticated machine with proven levels of performance and guaranteed safety margins. The jet airplane's performance and safety margins can only be realized, however, if the airplane is operated in strict compliance with the procedures and limitations contained in the FAA-approved Airplane Flight Manual for that particular airplane. The following information is generic in nature, and since most civilian jet airplanes require a minimum flight crew of 2 pilots, assumes a 2-pilot crew. If any of the following information conflicts with FAA-approved Airplane Flight Manual procedures for a particular airplane, the Airplane Flight Manual procedures take precedence. Also, if any of the following procedures differ from the FAA-approved procedures developed for use by a specific air operator and/or for use in an FAA-approved training center or pilot school curriculum, the FAA-approved procedures for that operator and/or training center, pilot school, take precedence. V-speeds. The following are speeds that will affect the jet airplane's takeoff performance. The jet airplane pilot must be thoroughly familiar with each of these speeds and how they are used in planning the takeoff. VS. Stall speed. V1. Critical engine failure speed or decision speed. Engine failure below this speed should result in an aborted takeoff. Above this speed, the takeoff run should be continued. VR. Speed at which the rotation of the airplane is initiated to takeoff attitude. This speed cannot be less than V1 or less than 1.05 times VMCA, minimum control speed in the air. On a single engine takeoff, it must also allow for the acceleration to V2 at the 35-foot height at the end of the runway. VLO, the speed at which the airplane first becomes airborne. This is an engineering term used when the airplane is certificated and must meet certain requirements. If it is not listed in the Airplane Flight Manual, it is within requirements and does not have to be taken into consideration by the pilot. V2, the takeoff safety speed, which must be attained at the 35-foot height at the end of the required runway distance. This is essentially the best single-engine angle of climb speed for the airplane and should be held until clearing obstacles after takeoff, or at least 400 feet above the ground. Pre-takeoff procedures. Takeoff data, including V1 over VR and V2 speeds, takeoff power settings, and required field length should be computed prior to each takeoff and recorded on a takeoff data card. These data will be based on airplane weight, runway length available, runway gradient, field temperature, field barometric pressure, wind, icing conditions, and runway condition. Both pilots should separately compute the takeoff data and cross-check it in the cockpit with the takeoff data card. A captain's briefing is an essential part of cockpit resource management, CRM, procedures and should be accomplished just prior to takeoff. See Figure 15-20. The captain's briefing is an opportunity to review crew coordination procedures for takeoff, which is always the most critical portion of a flight. Figure 15-20 text. Captain's briefing. I will advance the thrust levers. Follow me through on the thrust levers. Monitor all instruments and warning lights on the takeoff roll and call out any discrepancies or malfunctions observed prior to V1, and I will abort the takeoff. Stand by to arm thrust reversers on my command. Give me a visual and oral signal for the following: 80 knots, and I will disengage nose wheel steering. V1, and I will move my hand from thrust to yoke. VR, and I will rotate. In the event of engine failure at or after V1, I will continue the takeoff roll to VR, rotate, and establish V2 climb speed. I will identify the inoperative engine, and we will both verify, and I will accomplish the shutdown, or have you do it on my command. I will expect you to stand by on the appropriate emergency checklist. I will give you a visual and oral signal for gear retraction and for power settings after the takeoff. Our VFR emergency procedure is to. Our IFR emergency procedure is to. End of Figure 15-20 text. The takeoff and climb-out should be accomplished in accordance with the standard takeoff and departure profile developed for the particular make and model of airplane. See Figure 15-21. Takeoff roll. The entire runway length should be available for takeoff, especially if the pre-calculated takeoff performance shows the airplane to be limited by runway length or obstacles. After taxiing into position at the end of the runway, the airplane should be aligned in the center of the runway, allowing equal distance on either side. The brakes should be held while the thrust levers are brought to power setting beyond the bleed valve range, normally the vertical position, and the engines allowed to stabilize. The engine instrument should be checked for proper operation before the brakes are released or the power increased further. This procedure assures symmetrical thrust during the takeoff roll and aids in preventing overshooting the desired takeoff thrust setting. The brakes should then be released, and during the start of the takeoff roll, the thrust lever smoothly advanced to the pre-computed takeoff power setting. All final takeoff thrust adjustments should be made prior to reaching 60 knots. The final engine power adjustments are normally made by the pilot not flying. Once the thrust levers are set for takeoff power, they should not be readjusted after 60 knots. Retarding a thrust lever would only be necessary in case an engine exceeds a limitation such as ITT, fan, or turbine RPM. If sufficient runway length is available, a rolling takeoff may be made without stopping at the end of the runway. Using this procedure, as the airplane rolls onto the runway, the thrust lever should be smoothly advanced to the vertical position and the engines allowed to stabilize, and then proceed as in the static takeoff outlined above. Rolling takeoffs can also be made from the end of the runway by advancing the thrust levers from idle as the brakes are released. During the takeoff roll, the pilot flying should concentrate on directional control of the airplane. This is made somewhat easier because there's no torque produced yawing in a jet as there is in a propeller-driven airplane. The airplane must be maintained exactly on centerline with the wings level. This will automatically aid the pilot when contending with an engine failure. If a crosswind exists, the wings should be kept level by displacing the control wheel into the crosswind. During the takeoff roll, the primary responsibility of the pilot not flying is to closely monitor the aircraft systems and to call out the proper V speeds as directed in the captain's briefing. Slight forward pressure should be held on the control column to keep the nose wheel rolling firmly on the runway. If nose wheel steering is being utilized, the pilot flying should monitor the nose wheel steering to about 80 knots, or VMCG for the particular airplane, while the pilot not flying applies the forward pressure. After reaching VMCG, the pilot flying should bring his or her left hand up to the control wheel. The pilot's other hand should be on the thrust levers until at least V1 speed is attained. Although the pilot not flying maintains a check on the engine instruments throughout the takeoff roll, the pilot flying, pilot in command, makes the decision to continue or reject a takeoff for any reason. A decision to reject a takeoff will require immediate retarding of the thrust levers. The pilot not flying should call out V1. After passing V1 speed on the takeoff roll, it is no longer mandatory for the pilot flying to keep a hand on the thrust levers. The point for abort has passed, and both hands may be placed on the control wheel. As the airspeed approaches VR, the control column should be moved to a neutral position. As the pre-computed VR speed is attained, the pilot not flying should make the appropriate call out, and the pilot flying should smoothly rotate the airplane to the appropriate takeoff pitch attitude. Rotation and liftoff. Rotation and liftoff in a jet airplane should be considered a maneuver unto itself. It requires planning, precision, and a fine control touch. The objective is to initiate the rotation to takeoff pitch attitude exactly at VR, so that the airplane will accelerate through VLOF and attain V2 speed at 35 feet at the end of the runway. Rotation to the proper takeoff attitude too soon may extend the takeoff roll or cause an early liftoff, which will result in a lower rate of climb, and the predicted flight path will not be followed. A late rotation, on the other hand, will result in a longer takeoff roll, exceeding V2 speed, and a takeoff and climb path below the predicted path. Each airplane has its own specific takeoff pitch attitude, which remains constant regardless of weight. The takeoff pitch attitude in a jet airplane is normally between 10 degrees and 15 degrees nose up. The rotation to takeoff pitch attitude should be made smoothly but deliberately and at a constant rate. Depending on the particular airplane, the pilot should plan on a rate of pitch attitude increase of approximately 2.5 degrees to 3 degrees per second. In training, it is common for a pilot to overshoot VR and then overshoot V2 because the pilot not flying will call for rotation at or just past VR. The reaction of the pilot flying is to visually verify VR and then rotate. The airplane then leaves the ground at or above V2. The excess airspeed may be of little concern on the normal takeoff, but a delayed rotation can be critical when runway length or obstacle clearance is limited. It should be remembered that on some airplanes the all-engine takeoff can be more limiting than an engine-out takeoff in terms of obstacle clearance in the initial part of the climb-out. This is because of the rapidly increasing airspeed causing the achieved flight path to fall below the engine-out scheduled flight path unless care is taken to fly the correct speeds. The transitioning pilot should remember that rotation at the right speed and rate to the right attitude will get the airplane off the ground at the right speed and within the right distance. Initial climb. Once the proper pitch attitude is attained, it must be maintained. The initial climb after liftoff is done at this constant pitch attitude. Takeoff power is maintained and the airspeed allowed to accelerate. Landing gear retraction should be accomplished after a positive rate of climb has been established and confirmed. Remember that in some airplanes, gear retraction may temporarily increase the airplane drag while the landing gear doors open. Premature gear retraction may cause the airplane to settle back towards the runway surface. Remember also that because of ground effect, the vertical speed indicator and altimeter may not show a positive climb until the airplane is 35 to 50 feet above the runway. The climb pitch attitude should continue to be held and the airplane allowed to accelerate to flap retraction speed. However, the flaps should not be retracted until obstruction clearance altitude or 400 feet AGL has been passed. Ground effect and landing gear drag reduction results in a rapid acceleration during this phase of the takeoff and climb. Airspeed, altitude, climb rate, attitude, and heading must be monitored carefully. When the airplane settles down to a steady climb, longitudinal stick forces can be trimmed out. If a turn must be made during this phase of flight, no more than 15 degrees to 20 degrees of bank should be used. Because of the spiral instability and because at this point an accurate trim state on rudder and aileron has not yet been achieved, the bank angle should be carefully monitored throughout the turn. If a power reduction must be made, pitch attitude should be reduced simultaneously and the airplane monitored carefully so as to preclude entry into an inadvertent descent. When the airplane has attained a steady climb at the appropriate en route climb speed, it can be trimmed about all axes and the autopilot engaged. End Chapter 15, Part 4. Recording by Dale Latham.